Alright, so for our second problem, we'll start reading through this. It says 3 students are playing on an 8-meter, 50-kilogram seesaw. Jim is 120 kilograms and sitting 3 meters left of the pivot. Susan is 100 kilograms and sitting 2 meters left of the pivot. And Jumbo is 130 kilograms and sitting 3.5 meters right of the pivot. So first we're going to model the seesaw as a thin rod and find its moment of inertia. Great. So we'll draw a thin rod there and a pivot point. Probably should be somewhere in the middle, but we'll leave it right there. So we've got Jim. He is 3 meters over on the left. So got a nice little picture there. We'll model Jim as a box. Susan, 100 kilograms. Now, technically, if this pivot was in the middle, then there'd be 4 full meters, but you know, whatever. This is just sample drawing here. So Susan there, 100 kilograms, 2 meters, and Jumbo, 130 kilograms, 3.5 meters to the right of the pivot. Great. There we go. And we're modeling it. We've got the picture. So once again, from the textbook, we can find just the formula for the moment of inertia for pretty much, you know, all these different shapes. They've fortunately gone and found out for us what is the moment of inertia of a thin rod, and that happens to be 1/12 the mass of the object times its length squared. So that's really helpful for us. We'll just plug in the mass, 50 kilograms, plug in length, and we end up with 266.6. The units are kilogram meters per meters squared, rather. Part B. Find the net torque on the seesaw. Which way is it rotating? So let's talk about this just for a moment. So the net torque, obviously we've got Jim. He is sitting on it and is causing the seesaw to want to rotate this way. Susan over here, also on the same side, wanting it to rotate this way. This happens to be the positive direction. Jumbo, sitting over here on the other side, he is putting a force at a distance of that pivot, so he's causing a torque to be applied to this seesaw, and it's wanting to rotate the other way. So the question is, all right, we've got 2 people over here, one person over here, and you say, oh, well, surely because these 2 people are sitting over here, it's going to, the whole bar is going to start rotating like that. When in fact, well, we say, yeah, but Jumbo is, he's a little bit, he's heavier than both of them. He's 130 kilograms. And then you say, well, Jim's farther away. Well, not really. Jumbo's farther away than Jim. Okay, but there's Susan. So, all right, so it gets a little fuzzy. Which way is this thing actually going to rotate? And so what is the, when you add all of their forces at their distances, all those torques up, what's the net result? Okay, so that's what we're going to solve, and if it's positive or negative, that'll tell us which way it's rotating. So each one of these people, they're exerting a force downward due to gravity. It's their mass times their gravity, times the acceleration due to gravity. So the 2 on the left are causing it to rotate in a positive direction. Jumbo is causing it to rotate in a negative direction. So we could say torque 1 plus torque 2 minus torque 3. If you remember, the torque is the force, which is the weight force, times the distance that it is from the pivot. So I'm going to just call this R1. For Susan, I'll call that R2. For Jumbo, we'll call it R3. And I guess I didn't write it here. I should have written sine of theta. But in this case, since each one of them, for this initial moment, their weight force is pulling straight down, that is perpendicular to the lever here, and so that's going to be a right angle, at least initially, this first part right here. So times R3. So that's going to be 120 for Jim's mass times 9.8 acceleration due to gravity times the distance of 3, plus Susan, 100 kilograms times 9.8 times 2, which is her distance, minus Jumbo's weight, sorry, it's kind of hard to read here, but 130 kilograms times 9.8 meters per second squared at a distance of 3.5. And we end up with grand total of, drumroll please, 1,029 Newton meters, and that's positive, which means that Jim and Susan win. It's rotating their direction. It's rotating, due to them. So find the angular acceleration. Okay, so if there's a net torque, if the two of them together are working, then obviously this thing must have angular acceleration. Well, angular acceleration formula, Newton's second law, is equal to the net torque divided by the moment of inertia. What do you know? The two things that we had to find in parts A and B. So we just plug the numbers in there. That's the net torque. That's the moment of inertia. And turns out that this thing is rotating at 3.86 radians per second. All right. Then find Jumbo's tangential acceleration, which means how much he would be accelerating tangentially. If we draw that picture again here just real briefly, it's rotating this way, and tangential acceleration refers to his velocity each moment is going to be more and more and more, but his velocity is tangent, and so therefore he would have tangential acceleration. It's due to the fact that there's angular acceleration. And that formula, one of those linking formulas which relates linear motion to rotational motion, tangential acceleration a sub t is equal to r alpha. So there's the radius, there's alpha that we just found out. Sorry, 3.86 radians per second squared, and it equals 13.51 meters per second squared. That is Jumbo's tangential acceleration. All right, so once again, just drawing the picture, knowing the formulas, what to plug in where. These problems, hopefully, you'll find out after seeing a few of them in a row, are very straightforward. Thanks for watching.